In this video, we're going to look at why some chemical reactions are endothermic while other chemical reactions are exothermic. So if we look at the reaction that I've written out, okay, I've got reactant A reacting with my other reactant BC, and that gives me a product AB and another product C. So this is obviously just an imaginary reaction. And if I draw out what this reaction looks like, okay, I've just got A by itself, but I've got BC bonded together, which means there must be a bond holding B to C. On the right-hand side, I've got A bonded to B, so there must be a bond between A and B, and I've got C by itself. To get from the left-hand side to the right-hand side, you can see on the left-hand side, B and C are bonded together, but on the right-hand side, B and C are no longer bonded together. That tells me, in order to get from the left, my reactants, to the right, my products, I'm going to have to break that bond that's holding B and C together. The other thing I noticed, the other difference, is on the left-hand side, A is by itself, but on the right-hand side, it is bonded to B. So not only do I need to break the bond between B and C, but I need to form a new bond between A and B. And when we're looking at bond breaking and bond making, which I'm going to write a little bit further down here, bond breaking we'll look at first. If you want to break a bond, any chemical bond, that is going to require energy. You need to put energy in to break a bond. So I can say that bond breaking is endothermic. It requires energy. And then the opposite, if I'm making a new bond, bond making releases energy. So every bond that you break, it requires energy. Every bond that you make releases energy. So I can say bond making is exothermic. All I need to know is just how much energy it's going to take to break that bond between B and C. And what you'll be given is a little table that has bond type and then the energy associated with that type of bond. So my bond type in this case is my bond between B and C. And the energy associated with my bond between B and C, I'm just going to call it 500 kilojoules. Remember, joule is the unit for energy, and I'm just using kilojoules. And what this tells me is that if I were to break the bond between B and C, I would need 500 kilojoules of energy. And if I were to make a new bond between B and C, I would release 500 kilojoules of energy. So there's just one value for energy associated with one bond type, and that tells you how much energy would be required to break the bond or would be released if that bond were made. Okay, in my reaction, the other type of bond I'm looking at is AB. And let's just say that the energy associated with the AB bond is 700 kilojoules. So if I want to see if something is endothermic or exothermic, I need to look at how much energy I need to put in to break bonds, and then how much energy is released by all the new bonds that are formed. So if I look here at the left-hand side, how many bonds do I need to break? The bond I need to break is between B and C. And to break that bond, I need 500 kilojoules of energy. So for bond breaking, I need 500 kilojoules of energy. And then I look at the right-hand side and see what bonds I am making. And I see I'm making a new bond between A and B. And I can say that my bond making between A and B is going to release 700 kilojoules. So bond breaking, 500 kilojoules of energy is required. Bond making, 700 kilojoules of energy is released. And if your value for bond making, if your value for bond making is greater than the value for bond breaking, that tells you overall more energy is being released than is required. And if more energy is being released, then you are going to have an exothermic reaction. And if you wanted to put a value on this, we say that the overall energy change for the reaction is always the reactants minus the products. The value we calculated on the reactant side, the bonds were broken, was 500. The value we calculated on the right-hand side for bond making was 700. And you do 500 minus 700, gives you a value of minus 200 kilojoules of energy. And what this tells me is that more energy was released than was required. That, according to my equation, is going to give me a negative value. And anytime you have a negative value, you have got an exothermic reaction. So this reaction here is exothermic. Okay, so if I look at another reaction, this time I've got AB plus CD going to AC plus BD. And if I draw that out, I see I've got A and B bonded together, C is bonded to D, and on the right-hand side, I've got A bonded to C and B bonded to D. So to get from the left to the right, I will see on the left-hand side, A is bonded to B, but that bond must break because A and B are not still bonded together on the right-hand side. And again, on the left, I see I've got C and D bonded together. But again, on the right-hand side, C and D are not bonded together. So again, that's telling me that that bond must break for this reaction to take place. So I've got two bonds to break, but then I've got two new bonds to make. And I need to see how much energy I need to put in to break these two bonds, and then how much energy will be released when these two new bonds are made. So if I look at my bond breaking, I will see that the bonds I need to break are an AB bond and a CD bond. And if I, So I will see that I need to break an AB bond and a CD bond. And if I look over at my chart, I will see the energy required to break an AB bond is 700 kilojoules, and to break a CD bond is 300 kilojoules. So in total, the energy required to break bonds is 1000 kilojoules of energy. Now I need to look at how much energy is going to be released when I make new bonds. So I'm looking at my bond making. And the bonds I'm making are an AC bond and a BD bond. AC for my table. If I make an AC bond, I'm releasing 400 kilojoules of energy. If I make a BD bond, I'm releasing 500 kilojoules of energy. So overall, I see I'm releasing 900 kilojoules of energy. So for this reaction, I need to put in 1000 kilojoules of energy, and I'm going to get out 900 kilojoules of energy. So when I'm calculating my overall energy change, it's going to be reactants minus products. My reactants was 1000, my products 900, and my overall energy change is going to be 100 kilojoules. We saw above that when you get a negative value, that tells you it's an exothermic reaction. This time I've got a positive value, and when it's positive, it's endothermic. But the reason it's positive is not just because it's endothermic. It's not just because you come out with a positive value here. The reason you're coming out with a positive value is because you're putting more energy in to break bonds than you're getting released when new bonds are made. So overall, you have to put energy in for the reaction to take place. That means it's endothermic. In the above reaction, you had to put less energy in to break the bonds than you got released when new bonds were made. So overall, energy was being released. Because energy is being released, according to this equation, you get a negative value. That tells me it's exothermic. Down here, using this equation, I get a positive value, and that tells me that it's endothermic. So I'm going to do an example using a real chemical reaction this time. So I have drawn out my reactants on the left, and then you see I've got my product on the right. And again, I need to look at every bond that I have to break and every bond that I'm going to make. So on the left-hand side, I've got a carbon double bonded to a carbon. You can see on the right-hand side that that bond is not there. That tells me that that carbon-carbon bond, and I've got one, carbon-carbon double bond, and I've got one of them, has to break. I've also got carbon bonded to hydrogen. So I've got 4 bonds of a carbon to a hydrogen. So I've got one here, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. There are 4 carbon-hydrogen bonds. And if you look on the right-hand side, you've also got 4 carbon-hydrogen bonds. But in order to avoid mistakes, I would recommend just breaking every single bond in the reactants, calculating all of the energy, and then calculating all of the energy for all of the bonds formed. So don't look at what's different between reactants and products. Just break every single bond on the reactant side and make every single bond on the product side, and you'll avoid making mistakes. So I'm going to break this carbon-carbon double bond. I'm going to break this carbon-hydrogen bond, and I've got 4 of them to break. So I've got 4 carbon-hydrogen bonds to break, and then I've also got a bond between the 2 bromines, and I'm going to break that 1 bromine-bromine bond. So in general, because they will draw out these molecules for you, just count all of the bonds. And by bonds, I just mean the lines. So I've got 1, 2, 3, 4, 5, 6 bonds. So I need to break 6 bonds. I've got 1 and 4 is 5 and 1 is 6. So all of the bonds have been accounted for. On the right-hand side, what bonds am I making? Again, I'm just going to count up all the bonds. I've got 1, 2, 3, 4, 5, 6, 7 bonds that I'm making. If I look at those bonds, 1, 2, 3, 4 of them are carbon-hydrogen bonds. So I'm making 4 carbon-hydrogen bonds. I'm also making a carbon single bond carbon. And I'm making 2 carbon-bromine bonds. Now, I know you have got carbon-hydrogen on the left and carbon-hydrogen on the right. Could you just leave that out from both sides? Yes. But in other examples, you will see that it can be easier to spot what's different on left and right. So I would just recommend make a list of all of the bonds you've got on the left, all of the bonds you've got on the right, break all the ones on the left, make all the ones on the right, instead of trying to spot what's different. So if I need the values for breaking these bonds, okay, and I've got that here in a table. So you will notice that the carbon-carbon double bond and the carbon-carbon single bond are 2 separate types of bond, and they've got 2 different values. For my carbon-carbon double bond, the value is 614. For my carbon-hydrogen bond, my value is 413, and I've got 4 of them. So it's going to be 4 times 413 because I've got 4 carbon-hydrogen bonds to break. And then my bromine-bromine bond is 193. I need to add up all of those values to get the amount of energy needed to break bonds. And then on the other side, I've got 4 carbon-hydrogen bonds. So that's going to be 4 times 413. And I've got 1 carbon-carbon bond from my table is 348. And then I've got 2 carbon-bromine bonds, which is going to be 2 times 276. And again, I need to calculate the total value of energy released from making my new bonds. And when I do the calculations, I see that 2,552 kilojoules of energy is released from all the new bonds I'm making, but only 2,459 kilojoules of energy is required to break the bonds. So I am releasing more energy than I need to break the bonds. And when I plug this into my overall energy change, reactants minus products, I see I get a minus 93. Again, that minus sign telling me that this reaction is exothermic. Okay, it's exothermic because you're releasing more energy than you're putting in. Therefore, temperature is going to increase, and it's an exothermic reaction.